Many thanks for the kind invitation, and thanks to Benoit for inviting us to give these lectures. I think it's a wonderful idea, and we need more of it, because as knowledge across the full spectrum, natural, social, and human sciences, keeps growing at such an enormous, almost exponential rate, we start to know less and less about what everyone else knows. And so these deliberate initiatives to help us better understand all the other knowledge that's out there that our other colleagues are working on is really necessary and important. So this is a great series, and it's certainly an honor to be a part of it. So I want to talk about a paradigm, well, a couple paradigms. The old paradigm for physics and what it's been replaced with, or an old paradigm for physics, because there have been several over the ages. So classical theory, these are some of the old classic examples of what was a few of the details that needed to be resolved in physics over 100 years ago. I think we thought we mostly had it right, but there's a few puzzles remaining that physicists were struggling to resolve. So if you had a black body, so some object that didn't radiate any energy, but it was warm, and you wanted to understand what should be the equilibrium of energy, of the different frequencies of light in that box, microwave, infrared, different colors of the rainbow, ultraviolet, and so on. What should be the natural equilibrium? Well, what classical physics of the day predicted didn't make any sense. Right? The energies, the higher energy stuff should occur at a greater and greater intensity. You'd get some sort of catastrophe. There was this other the observed spectrum completely contradicted what the classical prediction said. You may have heard of the photoelectric effect, which Einstein resolved over 100 years ago. They were trying to explain why a low intensity light of one frequency was able to knock electrons off of a material, but you pick a lower frequency beam at a really, really high intensity. So you're really cranking this material with energy, and it wouldn't knock any electrons off. It didn't really make a lot of sense. The discrete spectrum of atomic radiation needed a new framework to explain stability of atoms. The traditional sort of Maxwell's equations predicted that the electrons should eventually, crash into the nuclei of atoms. And people always say, how come we don't see quantum mechanics day to day in our day-to-day lives? And I think we do, because do we see stable matter and people around us in day-to-day lives? Or we exist, so therefore the only reason we can have stable atoms is because of, classical mechanics didn't explain this. You need a quantum explanation for this. So there are all these puzzles that people were struggling with. Another day-to-day example where quantum mechanics is in action is if you have polarizing sunglasses, right? Have you ever worn your sunglasses and tried to read some kind of screen, realized it was black, but if you turned it 90 degrees, then you could see it? I don't know if you've ever noticed that. I thought something was wrong, but I took off the glasses and I could see the screen. It's because they filter all the photons, all the particles of light at one polarization, and then if you turn the other polarizer 90 degrees to that filters out the other polarization, and there'll be nothing left coming through both filters. If you ever try that with just two sunglasses, line them up 90 degrees to each other, it'll be black. So if I take two big sheets of this stuff, hold one in front of my face this way, and then another one the other way, you won't see my face. Okay, you don't need quantum mechanics for that. But you do need quantum mechanics for this puzzle, so you're sitting there, you're not seeing my face, all the light from my face to you is being filtered, then somebody puts another filter in between, it's 45 degrees. It's a filter, it just absorbs some of the light. And suddenly you can see my face again. Not at full intensity, but you can see it. So it doesn't make sense. Well, why would filtering more of the particles, you can try to come up with explanations, but ultimately there's a really simple quantum mechanical explanation. And my favorite example is what's called the Mach-Zehnder interferometer. It's a classic example of quantum mechanics in action. It wasn't one of the early puzzles people invented quantum mechanics to resolve, but it's one of the easiest ways to just explain the quantum mechanical paradigm. Imagine a source of particles, okay? So it could be photons, particles of light, so just like coming out of the ceiling here. If you turn down the intensity, eventually these particles are coming out one chunk at a time in discrete quanta. Or it could be electrons or neutrons, but the bigger the particle, the harder it is to do this experiment. You send it through, in the old days, it would be a half-silvered mirror. So, a normal mirror is just a piece of glass with silver on it. And just take off some of the, start with a clear, transparent piece of glass and start sprinkling silver on, but not too much. At some point, you'll get 50% reflection and 50% transmission. You have one of these things, you get a 50-50. In modern times, there's other materials that have the same effect. You don't need quantum mechanics for this. So then you set up this really simple experiment where you put one of these funny beam splitters, split the particles 50-50. These are just regular mirrors. Their goal is just to redirect the light. And then put through another one of these 50-50 splitters. So note that any particles, and they could be electrons, photons, that are coming up this way will get split 50-50. And any particles coming this way will get split 50-50. So conventional classical reasoning would say, well, if a particle goes here, there's a 50% chance it goes this way, and then times a 50% chance that it goes this way. So it's 50%, a 50% is 25%. So a quarter of the particles will go this way, a quarter will go this way, a quarter will go this way, and another quarter will go this way. They have two choices to make, 50% chance each way. Right? So there's 4 possible paths the particles can take. 2 of them end up here, 2 of them end up there. There's a 50% chance of ending up at each detector. Okay? But do the experiment, and under ideal conditions, all the particles end up here. And I can give you more examples of why this is unexpected, let's say. Okay. And this is a photo of an actual setup of this. Now these are high intensity beams in this picture, but you can do this one single particle at a time. Okay. So any sort of wave explanation just doesn't work. So it seems like a bit of a paradox, and you can try to patch it up, but not very naturally. So the classical reasoning we implicitly used there was that we have to make a choice when we reach the first beam splitter. So 50% of the time it goes along, say, the 0 path, and another 50% of the time it goes along the other path. And then we made another choice when we went through the other beam splitter, and there's another 2 branches. So there's a total of 4 paths here. Each path is taken with probability 50% times 50%, so 25%. A half times a half is a quarter. 2 of the paths ended up at one detector, which I'm just going to call the 0 detector. So and the other 2 ended up at the 1 detector. So the chance of ending up at the 0 detector is the sum of all the probabilities over all the paths that end up at the 0 detector. That was the reasoning we implicitly used. So a quarter plus a quarter is a half. That's why we predicted a 50% distribution. And the new quantum paradigm is almost the same, except it says instead of probabilities, you have these things called quantum probability amplitudes, which are ultimately the square roots, sort of like the square roots of probabilities. They're just numbers such that when you square them and take their absolute value, if necessary, it equals the probability. So it's saying there's a richer reality that explains classical probabilities. And to fully understand this experiment, you have to go into this richer reality. So the thing about square roots is they can be negative, right? What's the square root of 4? Well, it's 2, but it could also be minus 2. Square root of 2, well, we call it the square root of 2, because there's no other nice way to say it. There's minus square root of 2. And square root of a half is 1 over square root of 2 or minus 1 over square root of 2. So those 2 paths ending up in 0, one of them occurs with probability 1 over root 2 times 1 over root 2, which is a half. The other path occurs with amplitude 1 over root 2 times minus 1 over root 2, which is minus a half. So the probability amplitude of ending up at 0 is a half minus a half, so 0. If you want the probability, you square it. 0 squared is 0. Right? So it's a really simple set of rules. You might not believe them or have totally digested them, but it's just a really simple set of rules that predicts exactly what happens in that experiment. Okay? So it's just an alternative quantum explanation. So in between here, it's in some state which people struggle to understand what it really means, but in some meaningful way, it's along this path, which I'll call 1 with amplitude 1 over root 2, and in this one with amplitude 1 over root 2 at the same time. And the funny thing is, it could also be in a combination of 0, 1 over root 2, 0, minus 1 over root 2, 1. If you're in that combination, you'll end up over here. So 0 plus 1 is distinguishable from 0 minus 1. They'll each end up at different detectors. I'm not expecting you to be comfortable with this explanation, but it explains what you'll see, what that photo I showed you of a real experiment. And many of you maybe have seen the two-slit experiment. It's just a more complicated version of what I just told you. A particle coming out of a source could be going through one of these two slits, and they'll form a pattern on the screen. And you would think that if I block one of the slits and see the pattern, and I block the other slit and see the pattern, and then I unblock them, the pattern I see should just be the sum of the two patterns. But it's not. You get a different probability because every point on the screen is like one of those detectors in the previous experiment. There's two paths to get there, and the probabilities add up in this quantum mechanical way. You can have negative probabilities that cancel out. So you get this very unexpected pattern. Okay. I won't go through the mathematics. I just want to let you know that this is just, in fact, a more complicated version of this Mach-Zehnder experiment. So it's important to point out that what's really going on here is quantum mechanics is a new mathematical paradigm for expressing physical theories. So my favorite analogy is going from a flat Earth theory to a round Earth theory. Right? If you try to draw a map of the Earth, and you think the Earth's flat, it works for the most part until you really push it to the limits. You try to map out the whole Earth or a large part of the Earth, then it doesn't work. You get these paradoxes. Things just make no sense. Right? And what you didn't need a better understanding of the shape of Europe or anything. What you needed is to move away from a flat Earth mathematical framework to a spherical framework. So it's just a different set of mathematical rules. And that's all quantum mechanics was. It said instead of probabilities that are positive numbers that add up to 1, use these quantum amplitudes, which could be complex numbers, and their squares add up to 1. And there's some other rules, but to first order, that's the essence of quantum theory. So quantum theory is just a new mathematical paradigm that made a lot of physical puzzles solvable. It's a new paradigm, but it was not accepted immediately, even by some of its founders. So I'll give some Einstein quotes, because he's certainly by far the most famous scientist of the 20th century and one of the founders of quantum theory. He called it silly. He said it was useless, right? He was really bothered by this notion of these elements, what so-called elements of reality. Okay? He thought, because if you think back to that photon in one of two paths experiment, I told you that 0 plus 1 was perfectly distinguishable from 0 minus 1. Right? And if it is, the photon doesn't have a definite 0 or 1 state. But 1 is perfectly distinguishable from 0. And he was bothered by the fact that, when you think about it, it meant that a priori, that photon didn't actually have a well-defined value for both of those possible questions. Are you 0 plus 1 or 0 minus 1? Or the other question is, are you 0 or 1? Since they're both perfectly answerable questions separately, he thought they should have perfectly answerable questions together. And quantum theory said no, they're not both well-defined in advance. So that really bothered him because it contradicted some intuitive notion of just objective reality. And there's all sorts of these really wonderful quotes. You know, he laughs, I laugh only at the naivete of the proponents of quantum theory. Who knows who'll be laughing in the coming years? So I really like Max Planck's quote about that a new scientific truth does not triumph by convincing its opponents and making them see the light, but rather because its opponents eventually die and a new generation grows up that is familiar with it. And I think that's true with so many things. So eventually, the quantum mechanical paradigm has become the dominant paradigm for physics. And this new paradigm for physics, as I'll discuss in the second half of the talk, challenged the traditional paradigm for computation. That's what quantum computation is. So I'll stop there for now and invite Kieran to tell us a little bit about paradigms.
So how does this work? Okay. Thank you. I too am delighted to be here. I thank Benoit for putting on this very interesting lecture series on bridges and the idea of bridges. And when I was on sabbatical in New York, when this came up, and I remember emailing him saying, sorry, I can't make it to this first lecture. I can't remember who was doing it at the time, Benoit, but I just said, you know, maybe Mike Mosca and I, because we were colleagues and friends, and we kind of joked with each other. And at one point he said, let's do a lecture on the hermeneutics of quantum computing as a kind of a play off each other in terms of the idea of what reality is and what reality isn't. We both sort of worked with that idea. So Benoit took that joking comment and says, yeah, you're on. And so, and Mike, gracious enough to undertake this with somebody who works in the humanities and social sciences. So we met and we talked about this, and we agreed that one of the ways we could anchor the talk would be paradigms. And we talked about the idea of paradigms and paradigm shifts, and in the humanities and social sciences, it's a kind of a discipline in the broad sense where there's multiple paradigms and versus one paradigm. And so we said, okay, let's use that. And we were working out a title, and I don't know if you remember that old Recession song, Buddy, can you spare a dime? So my old teacher used to say, with regard to paradigm, Buddy, can you paradigm? I wanted that to be the title of the talk. And I thought we might have a much fuller room here if that was the title, but we agreed to settle on quantum computation and phenomenological hermeneutics. So I playfully set up the idea of how, if there are multiple paradigms, then is there a paradigm to assess paradigms? And then is that a paradigm anymore? So just playing around with that idea, and my graduate students will be familiar with this. This is the kind of, when I'm trying to introduce paradigms and paradigm shifts in my sociology classes, I talk about two main paradigms. A knowledge by discovery, which is essentially the dominant paradigm within the sciences, and the natural and the social sciences. And and then there's another paradigm, knowledge by interpretation. So we're talking about how knowledge gets created and the paradigms that will allow knowledge to be treated as knowledge of something true, knowledge of something real. So the knowledge by discovery is essentially the paradigm that's dominant in the sciences. It became dominant in the rise of modernity in the 16th, 17th century, and with especially with both the philosophers, Descartes, and scientists like Copernicus and Galileo. So the world, the assumptions, these are epistemological assumptions, that there's a world out there that lies in wait of discovery. It's out there, and we can get at it. How do we get at it? We get at it by observing. So we saw examples of what the complicated formulas that Mike was talking about. But he was talking about, here's the theory, but yet if we observe, we see different things happening. So, and that's the paradigm that says we check, we need methods, we need tools, we need ways of getting at the observation, but it's an observation of a world out there, and we're describing something. The idea is that knowledge aims at being objective and accurate. Is it, and can it be verified? So that would be the basic principles behind the knowledge by discovery that became the dominant paradigm in the 16th, 17th century over time. So examples, they would talk about how our senses mislead us. Our senses are deceptive. And this is why science is always sort of correcting common sense. Well, you think this is how it happens. But in actual fact, when we do tests, we find out it's different. So for example, this would be an example. I think Descartes used to talk about how you might put a stick in water and it'd look bent. But that's sort of an optical illusion. So we need ways of measuring it to find out if it really is bent or straight. So part of this would be that these three pillars look like they're different sizes. But in actual fact, they're the same size. And we would get that by measuring. So this Mueller-Lyer illusion, one line looks longer than the other, but they're the exact same length. And part of the idea here is this is why we need the tools to measure, the microscopes, the telescopes, etc., to measure, to see what is actually happening in the world and not rely on our senses. Now, let me move to another paradigm that is more prevalent in the humanities and social sciences. This says that it's not like there's a world out there lies in wait of discovery and we have to need the proper methods to get at it, but that reality and mind are interdependent. That anything known requires a knower, i.e. you can't get anything without a set of assumptions, without concepts. This means knowledge, from this perspective, is a product of a transaction between a knower who goes about investigating the world in a particular way with a particular set of assumptions and a known. This perspective says different observers will see different things because meanings are assigned differently, events are conceptualized differently. So knowledge, from this perspective, is shaped by pre-understandings. The pre-understandings that we bring, including the epistemological pre-understandings that the scientific paradigm brings. So from this perspective, to know is to understand the understandings, the pre-understandings, which made the knowledge possible. All knowledge relies on pre-understandings. The idea of scientific objectivity from this perspective is a specific type of knowledge. It's not that it's not knowledge, it's a specific type of knowledge. And it reproduces a specific understanding of the world. So the aim, from an interpretive point of view, would be to reflexively identify the powers and limitations of the various ways of knowing the world, which would include reflexively identifying the powers and limitations of the scientific model. So here we have examples. This is Wittgenstein's famous duck rabbit, which was actually developed from Jastrow's duck rabbit. So I'll use Wittgenstein's, nice and simple. So we have here a rabbit and a duck. Is this a bill, or are these ears? Well, it depends on the assumptions you bring. If you were to see it, if we start looking at it as a bill, then we'll see a duck. If we start looking at it as ears, we see rabbit. This becomes a mouth versus the back of a head. Now, is there one that's right? It depends on it depends on the assumptions you're bringing. Here is a more interesting one. This is an old lady and a young woman. That's the old lady. So, can I ask, who sees the old lady? Who sees the young woman? Who only sees one? So, which one? Jim, which one do you see? The old lady. So, and this is, so again, this is part of the idea. Is this a nose or is it a chin? Is this an ear? Is this an ear? Or is it an eye? If you're looking at the young lady, it's an eye. Or it's an ear, sorry. If you're looking at the old lady, it's an eye. So both exist simultaneously. So this is just an illustration of how there are multiple paradigms, how for us to know this means we have to know young ladies, old ladies. We have to know ducks and rabbits and know how we can, through those pre-understandings, we can bring and recognize and be able to say it is one or the other. So let me just briefly, this is a brief outline of the history of sociology. So unlike science, sociology and humanities tend not to forget the beginners. They continue to be alive and be revisited again and again. So sociology, this is how I ended up doing the kind of work I did. Sociology, founder Max Weber. He founded he defined sociology as the interpretive understanding of social action. And he defined social action as action where individuals take the other's behavior into account and orient accordingly. So humans are beings who take each other's behavior into account. And insofar as we take each other's behavior into account, that influences the action. So simultaneously, around a little later, continental philosophy, Husserl was solving some problems in mathematics and philosophy, developed modern phenomenology. The problems that he was working on eventually got solved as Gödel's theorem. Alfred Schutz, he was a Jewish refugee who left Austria during the Second World War, came to North America. He was a student influenced highly by Husserl, but also used what he learned from Husserl to re-engage Weber's work and developed a phenomenological sociology, who in turn influenced Harold Garfinkel, who developed this in sociology, a school called ethnomethodology. Garfinkel influenced Blum and McHugh, who were my teachers. Martin Heidegger, who was a student of Husserl, and developed a phenomenological hermeneutics. So it took phenomenology and pushed it in a more hermeneutic direction. His students were Hannah Arendt, whose famous work as the Eichmann, a study on the banality of evil. She came up with the phrase, the banality of evil. She also studied totalitarianism from, again, a German Jewish refugee to the States. Another of his students, Hans-Georg Gadamer, who actually lived 100 years, so got to write a lot, from 1900 to 2002. My teachers, Blum and McHugh, Gadamer used Heidegger to re-engage Plato and say Plato now provides a way to re-engage social inquiry. So he was enlivened in a different way. Blum and McHugh were doing that simultaneously. And so when I came to York University in Toronto, and from Ireland to study for a master's, I told my wife we're just coming for 2 years, 33 years ago. I came thinking that I was going to be reading a lot of Heidegger, and it turns out I ended up reading a lot of Plato. and seeing how Plato is being applied to help understand contemporary social issues. So I'll briefly go through this. Edmund Husserl, what was his idea is consciousness is not blank that we have to test in order to see, observe certain problems. Rather, consciousness is always intentional. We're always out there, we're looking. Perceptions are molded by concepts. So if I take Alfred Schutz, taking what Husserl had said that the everyday life world depends on the natural attitude. And the natural attitude is the world is experienced in ordinary everyday ways where appearances, until further notices, are treated as reality. That's a feature of the organization of everyday life. So that the presumptions is things are as they appear. Wittgenstein used to had this in his famous book, Philosophical Investigations. Imagine the person who every morning before they open their door, they wonder if there's going to be a chasm at the other side of the door. So they always open the door, look, check, oh, fine, and then proceed out. And then Wittgenstein says, maybe someday he'll be right. But part of the idea is that's not how we do everyday life. We don't check everything. We're not suspicious. In fact, it takes a special motive to introduce the art of doubt or the art of suspicion. And everyday life depends on us taking appearances as they are. Intersubjectivity is the world is experienced, is shared with other experiencing subjects, which includes the reciprocity of perspectives. I assume that you know my role as a lecturer, and you're assuming that your role as a listener. And I know you know that, you know I know that, I know you know I know that, and you know I know you know that. That's part of the reciprocity of perspectives. That to sustain it, we're able to sustain each other's, a world that emerges out of our assumptions that we make of each other and each other's actions. So science, from Schutz's perspective, adopts a theoretical attitude. So for science to happen, you take a theoretical attitude, which is to say, you doubt everything and test it to see if it can be reproduced, verified, etc. The critique within the social sciences is that sociologists were testing things like the influence of class, race, gender, the patterns of social action over time, etc. And from a phenomenological perspective, what social science is doing, explaining a world that's already explained, exists, and is reproduced by everyday members. And what phenomenology has to do is to describe the first order of explanation, which is how come we have a world to investigate in the first place, made up of classes, races, creeds, religions, a world that's been reproduced in ordinary, taken for granted ways, that is treated as the ordinary world that it is, such that it can be subject to scientific explanation. So, Garfinkel and ethno methodology. One of the things that he, in his research, he took Schutz and applied them and says, every account is reflexive of the setting in which it happens. My description here of a lecture assumes, and we all assume, that what's involved in this lecture, what's involved in constituting this reality. So I'm talking, there's listening, there's following or not following, there's engagement or lack. If all of a sudden the fire alarm goes off, that fire alarm reconstitutes the activity that we're in. It actually reconstitutes it, and now we in turn will look at that fire alarm and act, walk slowly out, etc., in order to see that the activity that we're engaged in is different now by virtue of that fire alarm. And we're orienting to each other in order to be able to establish this. If all of a sudden something fell through the roof here, but St. Jerome's is in very good shape in its building, so we don't have deferred maintenance, so this is why that won't happen. But if something fell through the roof, all of a sudden we'd be going, what's happening? And we would be in the active sense of making sense of it. Garfinkel introduced the term breaching experiment to try and test the taken for granted assumptions that everyday life rests on. The most famous breaching experiment is, or an example of, is he asked students, when somebody greets you, just ask them to clarify what they mean. Simple, a simple issue of clarification. Here was one student who was the subject, how are you? Oh, sorry, the subject, how are you? And the experiment, how am I in regard to what? My health, my finances, my schoolwork, my peace of mind, my red in the face and suddenly out of control. Look, I was just trying to be polite. Frankly, I don't give a damn how you are. Part of the idea is everyone knows how are you a greeting is and what the response of a greeting. And the idea of just asking a clarification question already makes that greeting impossible. You know what it is. I know you know what it is. I know you know I know what it is. And if you're not engaged in the socially sanctioned discourse of doing a greeting, then you're playing another game. And what is that other game? So now this ethnomethodology has actually had a huge influence on the study of human-computer interaction and computer-supported cooperative work, CSCW. So it's actually had a huge influence on system design. For example, there's this article by Paul Durish and Graham Button. They're hired by Xerox, they're hired by Microsoft, they're hired by Xerox, Microsoft, and Apple. And they show what's involved, because everyday life is so complicated and has so many assumptions built into it. When somebody is designing something, they need to know how is it going to be adopted into everyday life. And so part of the design imagines people integrating it into their everyday life. So ethnomethodology became prominent in the design and analysis of interactive systems. And this is a condensed abstract, they say that it actually has a foundational place, so that in the idea of design, you're always thinking of a potential user, somebody who's engaged in everyday life and how they might use it. And insofar as you're doing this, you're drawing on your ordinary, everyday, taken for granted assumptions that make everyday life possible. This is another one, design in the absence of practice, breaching experiments. This Andy Crabtree, and these were engineers and computer scientists who then got interested in ethnomethodology through their engineering and computer science by virtue of the fact, as they were dealing with real problems of design, realized that ethnomethodology would help with this. So this is a study on the new mobile multiple interactive games that, and how people engage in this. And so how do people, very often you're saying, okay, we're going to introduce this, and this is both for marketing and for design of a new technology. How is it going to be incorporated? How are people going to engage it in their practice? Because if it's not, then it fails. It might be a nice invention, but insofar as it's not incorporated, because people can't imagine ways of using it in ordinary everyday life. I was just describing in my classroom today about the example of how these technologies change how we just even walk on the street. How the idea of the mobile phone, the BlackBerry, the iPhone, you might, when you're walking down the street in a city and you see somebody coming towards you, and they're talking away, blah, 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 you know. So you know there's a couple of possibilities. Might be somebody who's crazy, and the city includes people who are crazy, and that will mean once you kind of try to see what's going on, that talking, You say, okay, just going to take a little wide berth here, because we don't want to encounter and create a scene with a crazy person. But then as you're approaching, you're saying, oh no, this sounds like a normal conversation. And then you notice they have earphones. And you know, oh, so they're having a telephone conversation. Now, part of the new technology includes the idea of how we adjust to walking on the street, hearing people what looks like talking to themselves. And are they engaged in a rational, reasonable activity, or are they in fact crazy? And we constantly make these decisions as ordinary, everyday members. So here, this was the development of a mixed reality, tangible, ambient, ubiquitous, mobile, wearable computing have seen the emergence of a range of technological innovations that have little or no grounding in current practices. In other words, this isn't actually engaged in modifying existing practices like the mobile phone, which has modified the telephone, but rather it's creating new practice. How do you test for that? So what Crabtree did is just, it was an interactive game, and I'll just briefly describe it, where there are players, 6 players, there's a map of a street, and then there are runners actually on this street in Sheffield. And the runner's task is to reach where the players are moving around electronically. The runners have walkie-talkies, and they have GPSs. And they're looking for where the runners are. They're watching the same screen as the players on the actual street, and the runners, if they can catch the actual real runners, catch the avatars, the people are out of the game. And that was this game. And so part of what they were testing is how runners make sense of what they were doing because of the inaccuracy of the GPS. GPS, because of the Earth's curve, etc., didn't actually locate people very precisely. But the runners were using their local knowledge of the street to be able to anticipate where the avatars might go, and we're able to, on the whole, very easily, by collaborating, catch all the avatars and eliminate the players. So that is, again, and this is now a little ad, it turns out there's a conference coming up, the International Institute for Ethnomethodology and Conversational Analysis. It's an international conference every 2 years, and it's having, 2 years ago it was in Switzerland, the conference. This year it's at Wilfrid Laurier, University of Waterloo, St. Jerome's. And and so there'll be people who'll be studying this human-computer interaction. It's on technology and techniques. And it's one of the, Wes Sharrock, one of the ethnomethodologists, most prominent ethnomethodologists in England, and he accepted a 2011 Lifetime Achievement Award from the American Sociological Association. And he says, it's been to ethnomethodology's credit that the subjects we've studied in the field of science and technology thought that ethnomethodology was sociology. So, back to Michael.
So in the first part of the talk, I explained how the old paradigm, we really liked it until it just wasn't, we couldn't solve some important puzzles in the old paradigm. So people fished around for another model that would be able to resolve the puzzles and still explain everything else we already knew. And it wasn't immediately accepted. And for one of the reasons, although it resolved some of the puzzles that people had been grappling with, it had other implications they were not expecting. Right? So again, like Einstein, a particle, it can have a definite position, it can have a definite momentum, but quantum mechanics said you can't simultaneously have a definite position and a definite momentum, which was very counterintuitive. So there was other consequences. So although it solved all these puzzles for us, then it opened up all these other consequences that people were just not so happy with. So then they were struggling to say, well, maybe there is some other, we got to work harder with the classical paradigm to solve those puzzles and just not have to embrace this new paradigm. And the discussions and debates continued for decades. John Bell, an Irish physicist who worked in Geneva, he proposed an experiment that would actually distinguish, right? So ideally what we'd like is, here's one paradigm, here's another, which one's right? It'd be nice if there was some experiment that could distinguish the two, and then you do the experiment, and that would hopefully, settle it. In practice, it wouldn't necessarily, because people would maybe still try to find some other way around accepting the consequences of the new paradigm, but it would start, at least move everything in that direction. I'll rephrase the test that John Bell came up with as a game. I'll give you the computer science version. There's a physics version as well, but I'm really a mathematician who does theoretical computer science in a new quantum mechanical framework. So try playing. You can actually play this game. It takes 3 or more people. You take find an Alice and a Bob, and you separate them. Okay, it's 2 separate rooms. And you challenge Alice and Bob. You give them a list of bits, input bits. You give Alice a bit S, and Bob a challenge bit T. So a 0 or a 1. Okay. And then once Alice gets her input, she has to output a bit, a 0 or a 1. And Bob does the same thing, but they're separated. They have no idea what's going on in the other room. It's like when the police arrest 2 collaborating criminals and they interview them separately, okay? Because they don't want them to communicate and coordinate their answers. The goal is, so they can't communicate, the goal is that they always give the same answer. Now that would be easy. Always give the same answer, except if they were both asked the question 1. If they're both given the input bit 1, then they have to give the opposite answer. Otherwise, give the same answer. And there's the dilemma. Okay? So here's so if Alice is given, these are the possible challenges to Alice, 0 or 1, Bob is 0 or 1. So if they're both given 0s, they can output anything they like as long as it's the same. Likewise. So as long as one of them is given a 0, they have to give the same answer. But if one of them if they're both given 1s, they have to give opposite answers. So imagine you're Bob, you're given a 1. Well, you don't know if Alice was given a 0 or a 1. So you can easily win this game 3/4 of the time by just agreeing you're always going to say 0. As long as you always agree. So you can win this game 3/4 of the time by always just giving the same answer. If they always output 0, for example, they'll win in all 3 of these cases, but they'll lose in this case. You can randomize it. You can always come up with Alice and Bob can come up with a strategy, so they always win 3 out of 4 times. And it turns out, there's a well-known theorem that that's the best they could ever do. So if they want to win this game as much as possible, if they cheat, they exchange notes in advance, they come up with whatever clever strategy they like, they can only ever win with probability 75%. That's in a classical paradigm. If they share one of these entangled states, so an equally weighted, what we call superposition of either having both 0 or both 1, so it's this funny quantum state that Einstein and others they said quantum mechanics is so ridiculous because it predicts the existence of these states, and there's certain outcomes. If you measure one half of the state, it affects the correlations when someone else measures the other half of the state. He called it spooky action at a distance. He said it's just so ridiculous, there's something wrong with this paradigm. Turns out that's exactly what happens when you do the experiments. But if you use one of these, so if Alice and Bob so let's say that everyone thinks the world's classical, but they happen to know it's quantum. They could exchange some quantum particles in these states, and they can actually win the game 85% of the time. So if you repeat this 1,000,000 times, okay, and you win 85% of the time, that's just impossible. Like essentially, the probability of that happening is essentially 0 in the classical world. So here's a very simple, well-defined game, a test, where if the world is truly classical, and that's what many people were struggling to recover. They were glad to solve those puzzles, but then the implications were so unpleasant, they were hoping to come up with another classical explanation. And they did come up with some not so natural classical explanations. which predicted you can't win this game any more than 75% of the time. And this new quantum theory said, actually, you can win it 85% of the time. That's what John Bell showed. So the Bell inequality, you can reformulate it to say the probability of winning this game is at most 75%. But he came up with an experiment that would win it 85% of the time. And this was in the 60s. And in the early 80s, technology wasn't available then. But by the early 80s, Alain Aspect in France actually played this game. And Alice and Bob won 85% of the time. So he ruled out this huge class of classical theories called local hidden variable theories that many people were arguing for. There's this quantum stuff, it's too weird, don't like the implications. Here's another, maybe not so elegant, but plausible explanation. And people were arguing about them. He proposed an experiment. Alain Aspect did the experiment. And a really curious, really interesting story. Lynn Watt, who was a professor in our engineering faculty, very distinguished colleague who passed away recently, he was teaching here in the early 80s. He was teaching Mike Lazaridis and others, standard engineering course, and he had extra lectures to talk about these experiments, these Bell inequalities and these experiments. And Mike, amongst the others, were fascinated by this. And this was one of the things that piqued Mike's interest in theoretical physics and later inspired him to found the Perimeter Institute and the Institute for Quantum Computing. So, most physicists were working in the quantum paradigm already. But there were still people who were not so happy about it. And certainly Alain Aspect's experiments helped convince people that the quantum paradigm is probably the right one. And in the early 70s, people were already starting to use it or think about its implications for other things, other aspects of our lives. Suppose, one problem with money is you can, in principle, counterfeit it. And you may have heard of the Heisenberg uncertainty principle. If you measure a quantum system, you have to disturb it. It has other implications, which means you can't clone quantum systems. Because if you could clone them, you could clone it, measure one of them, and you still have the good copy, right? So you can't clone. So if you could make money out of quantum particles, you can't counterfeit it. So he proposed this, in principle, quantum money scheme. Brilliant idea, deep insight. And it was rejected, and he kept it in his drawer. He did tell Charlie Bennett about it at IBM. And Charlie Bennett bumped into, literally, Gilles Brassard, a cryptographer, and told him about this idea. And together they came up with another application based on Wiesner's idea called quantum key establishment. Well, they called it quantum key distribution. And this is in contrast with what we do every day on the internet. We do classical key establishment. The classical key establishment we use all the time relies on a hard mathematical problem. It relies on something like factoring being hard. So it's easy to take two numbers and multiply them together. We could do that very fast. But if I give you a very big number and I say what are its prime factors, that becomes a very hard problem as the number gets big. 1,000 bits, a few hundred digits, and it's intractable for our computers. So the internet is secure because this problem is hard. Okay, the only reason, when you download daily your software updates, whether it's your browser or your operating system, your antivirus software daily, you have to know, how do you know that that's Microsoft or your antivirus company or Adobe or whatever? How do you know? Well, you don't. Your software is doing it for you. They're verifying it based on the hardness of problems like this. When you're doing online shopping and online banking, you negotiate a key, which you then use to encrypt your credit card and so on. It's all based on hard mathematical problems. They proposed a new way to do it based on, instead of hoping that these problems are hard, let's just use the uncertainty principle. Let's use the laws of physics to give us the security. If somebody's eavesdropping on our key, they will disturb it, and then I won't use the key. So they came up with an unbreakable way to exchange information securely on the internet, if you have a quantum internet, a quantum compatible internet. So all these new ideas were coming in this new, it was a totally new paradigm. There's a whole new set of rules to the game. Okay. completely uncharted territory. And they were the first few pioneers to do so. And to first order, nobody cared. Probably to second order, nobody cared. They were a little more persistent and were pushing this idea, and they eventually got it published. Not in a terribly prestigious, it was just, they got it published somewhere. Okay? It started to gain a little respectability in the early 90s or so when people started actually physically implementing the protocol. Because then suddenly it didn't seem like crazy science fiction anymore. There's real prototypes. They weren't very good prototypes, but they were physical prototypes. Still not widely adopted because although it was better than what was being used still worked. So why bother? That changed in '94 when Peter Shor said, this quantum paradigm, this factoring problem I told you was believed to be hard, actually it's easy in the quantum paradigm. Well, that's not good. We just bet the whole information security infrastructure on these problems being hard. But that was all seemed true in the classical paradigm. Now they're easy. But we don't have quantum computers yet. The existence of quantum computers still seemed like science fiction. Not many people had really been thinking about them. So there was no mass panic, but people did start wondering, wait, so are these things for real? Can you really build them? Is this paradigm really okay? More and more people started to care. And this quantum key distribution alternative started to have commercial prototypes with modest sales, but still not widely deployed. I haven't told you what a quantum computer is. I've alluded to it. It's really simple. Information is ultimately stored in a physical medium. It's manipulated by physical processes. So you can't have a meaningful theory of information processing, of computation, unless it's cast in some realistic physical framework. And we used to think in classical terms, but physics is actually quantum as far as we can tell. That's the best paradigm we have. So you have to reformulate. You have to double check and make sure that in this new paradigm, nothing dramatic happens. But something dramatic does seem to happen. Quantum computers seem to be exponentially more powerful than classical ones. Not what we necessarily expected or hoped for. I don't know if we hoped for, but not what we expected. Why is it exponentially more powerful? Because 3 bits, say you have 3 atoms, which can be in a 0, an electron can be in the ground state or excited state. It's a simple way to encode a bit. So 3 electrons, if you want to fully describe, so 3 atoms, so 3 bits, if you want to fully describe their quantum state, you need to tell me the probability, that quantum probability amplitude of all the configurations. Because there's 8 possible configurations of 3 bits. 0, 0, 0, 0, 0, 1, and so on. Sorry, these things didn't get toggled. They should all be in the different configurations. 0, 0, 0, 0, 0, 1, and so on. And then 1, 1, 1 at the end. Okay? And so these numbers, if you square them and add them up, they equal roughly 1. If you want to simulate on a classical computer this simple quantum system, it's just 3 atoms. And it's not even the full atom. It's just one particular property of these atoms. You need to keep track of 8 numbers to pretty high precision. Right? You could do that, but if you have 10 bits, quantum bits, you need 2 to the 10 numbers, so it's about 1,000. 20, you need 2 to the 20, it's about 1 million. Right? To keep track of 2 to the 30 numbers, that's 1 billion. Right? 2 to the 50, we're talking petabytes. And that's just 50. So you can see the exponential growth in the amount of classical memory needed to simulate a small number of quantum systems. So there seems to be this potential, this exponential complexity in a quantum system. And the quantum paradigm seems exponentially more powerful for computation than the classical paradigm. There was all this exponential power all around us, and we didn't know it. And this challenged one of the fundamental tenets of theoretical computer science, the foundations of computing. We used to think that a classical computer, and that's just a realization of what would be called a probabilistic Turing machine, could efficiently simulate any realistic model of computing. But a classical computer can't simulate even 100 quantum particles. So if you build a computer out of quantum particles, you can't simulate it with a classical computer, which violates this fundamental theorem. That's not a theorem, sorry, this thesis. It's just an assumption underlying computation. The intuition behind the assumption is very natural and believable, right? Because as long as your classical computer, your regular computer, can simulate any physical system efficiently, well, some other computer is just a physical system evolving according to some rules. So as long as your computer can simulate physics, it can simulate any other computer. But our classical computers, right, something stuck in the old classical paradigm is not powerful enough to simulate a computer in this richer quantum paradigm. But the idea behind the Church-Turing thesis was sound. That for any physical paradigm, there exists a computing model that captures the computing power of that physical paradigm. Right? So the idea is fine, you just have to define a computer that captures the power of quantum physics. This is what David Deutsch articulated in the mid-'80s. But this was a shocker, right? Because we all assumed, we took this for granted, essentially. Right? And there's this fundamental principle for humans, and that's, Wim van Dam told me this equation once. He told me that if A implies B, so if some proposition implies some other proposition, and B is unpleasant, well then A is false. Okay? So everything, you can agree with everything as you go along, but then as soon as you realize the implications are on something you don't like, you immediately go back to those assumptions and say, okay, well, which one of these is wrong, right? Must be wrong. So we do this I do it, we all do this all the time. So here's another unpleasant implication. Again, the physicists were concerned about objective reality, and the computer scientists were concerned about, the Church-Turing thesis. So certainly, it was not something that, I initially was very skeptical about quantum computing until I looked at it more closely. But fundamentally, the idea was sound. You just had to reformulate it in the proper paradigm. And that says that a quantum computer can efficiently simulate any realistic model of computing, which completely makes sense now in hindsight to me. Right? People, inevitably will ask, well, what does a quantum computer look like? Well, we don't know because we haven't really built large quantum computers yet. But they could, for example, be trapped ions. So these could be, ions of various flavors, beryllium, for example, calcium, trapped in some electromagnetic potential. This is all the physics underlying it. But if you look deep inside your classical computers, it'll look like something foreign to most of us as well. Right? Essentially, long term, we're moving towards just harnessing thousands, millions, hopefully millions someday of these on some two-dimensional structure. Here's a chip that can control many of them. So eventually it'll just be a chip inside a box that you don't see. Okay? Or maybe superconducting qubits. We're still trying to find the right physical medium for building these quantum computers. Physics tells you that it's possible, it doesn't tell you how to do it. So these are literally just little circuits, electrical circuits. You put what's called the Josephson junction in there. It gives it the right structure so that you can code a bit in there. Again, this just looks like a physics experiment. People are moving towards integrating them on chips. Here's 4 quantum bits. Again, the goal long term is to integrate thousands, even millions of them. We're a long way away from doing that. Individual parts aren't working quite well enough to be able to scale them, but my colleagues are getting impressively closer and closer. We don't know when they'll reach that point, but people are getting more and more optimistic, or certainly encouraged by all the progress. There was a Nobel Prize in the last year. 2 of our colleagues, one works on ion traps, the other works in cavity quantum electrodynamics. Why would you want to build a quantum computer? I just told you it's exponentially more powerful, but for what? It's not exponentially faster at anything. It's exponentially more powerful at certain things. Simulating quantum materials. This is what Richard Feynman proposed, right? Simulating simple collections of quantum particles. Why would you want to do that? If you're trying to understand the properties of quantum materials, superconductors. You're trying to make better energy transmission lines, or room temperature superconductors and so on. You want to be able to simulate these things so you can design them better. It's hard to simulate quantum materials because of all these quantum effects, but a quantum computer can often simulate them exponentially better. Also, a wide range of optimization problems. Okay, there's a lot of computing power expended today trying to optimize processes, resource allocation, and so on, and we can speed that up. We can solve these, what might seem esoteric mathematical problems, but a lot of them underlie internet security. But ultimately, I think we haven't even discovered most of the applications. This is just what we can think of today. We certainly hadn't thought of most of the applications of today's computers 50 years ago, or even 20 years ago. So one thing I personally spend a lot of time on is reassessing security, computational security, cybersecurity, in a quantum paradigm. We need to transition the current way of doing things over to a new set of tools that will be safe against quantum computers. And it's a very long road. Okay? There's a lot of reasons why people just, they don't want to believe the new paradigm, and then they're hoping someone else will do it, or they'll retire before they need to do it, and so on. But that's a very active and important area of work. So I talked about quantum computation. I've also talked about how it'll transform cryptography, this new paradigm for processing information. It'll also transform other forms of communication, distributed computation, and perhaps the earliest. So I started with the most ambitious end goal, but on the path, so there was a new paradigm. We understood, we observed quantum systems, quantum effects. We started to understand them. Eventually we moved on to controlling them. This is a general pattern in science. Understand, there's a problem, new paradigm, new solution. Then we observe things, we test, and then we start controlling. Right? And the first generation of things, so I mentioned that, quantum particles are very sensitive. You just disturb them just slightly, right? They're very, very fragile, which maybe makes them good sensors. So if you're trying to very precisely measure time or frequency, if you're trying to detect magnetic fields, so the way oil exploration is often done is you'll send this probe and you'll do magnetic resonance to image what's down there. And if you use the quantum properties of the probe, you get a much better image. So one of my colleagues, David Corey, works on that. Better medicine, better medical imaging. Could you imagine less invasive and more accurate imaging by exploiting the quantum mechanical properties of the probes or of what's being probed? So that's the sort of the more first generation type technologies, because we don't need large scale quantum devices. You can do this with small scale quantum devices. And that power was always there. I mean, MRI has been around for decades. Right? Only recently, in the last 10 to 15 years, have we started exploiting the quantum properties. I mean, we were, but now we're, more deliberately exploiting the quantum properties in more imaginative ways. And again, I think there's going to be all sorts of future discoveries. As we start putting these devices into the hands of students, undergraduates, they'll come up with all sorts of applications, just like we did with classical computers here in Waterloo in the 60s. And we put them in the hands of undergraduates, and they started doing all sorts of amazing things with them. So it's starting now, as we get a greater and greater collection of quantum tools, we'll have a new generation of scientists and engineers doing all sorts of interesting and important things with them. So an important point I want to make then is that quantum computing, or more generally quantum information processing, quantum information science and technology, is not about one specific problem or one specific technology. It's about harnessing a whole new paradigm, right, and seeing what it offers us. So the applications areas are unbounded, and we're just starting to explore them, because it's not about a specific thing. It's about harnessing an entirely new paradigm. So we often talk about, well, with this new paradigm, we get a new understanding, we're able to control, we can now solve new problems, create prosperity and better healthcare and so on. That's all tremendously important already, it also provides a deeper understanding of the paradigm. There's this new paradigm, trying to make sense of it. One way to make sense of it is to see what its implications are. So understanding its implications for all these information processing tasks is one way to better understand the underlying paradigm, which then better informs us for all the other applications of the paradigm, non-information processing applications. It also gives us a new way to test the paradigm. So one of my colleagues says, the main reason we want to build a quantum computer is to test the paradigm. Because quantum mechanics makes this completely audacious prediction that there's this exponential power lurking in the universe that we hadn't realized was under our noses. So that's a pretty audacious prediction of the physical theory, of the new paradigm. That needs to be tested. You can't just take it for granted. That needs to be tested. So maybe one of the most interesting things we'll get by building large-scale quantum computers, hopefully someday, I'm personally very optimistic, is just confirming the paradigm to a degree that has never been tested before. And we're very fortunate here in Waterloo to have had many people supporting our work exploring these new paradigms. So I work part-time at the Perimeter Institute, where we're probing the foundations of physics itself. There are people who are trying to understand this quantum mechanical paradigm, people studying gravity and other things, just the fabric of physics itself. And at IQC, at the Institute for Quantum Computing, we study also the foundations of quantum information, again, which is information theory reformulated in this new physical paradigm, its foundations, its applications, and also we're building them and implementing things. So I have many supporters from around Canada and abroad. So I think I'll invite Kieran now back up to the podium.
What's interesting about this, thanks Michael, what's interesting about this for us is that we're more or less seeing each other's presentation for the first time. We kind of understand where we're coming from, but we also know that we're operating in a sense on several different paradigms. Thank you for this ruler, Conrad. Conrad told me to say that, again, the math department saved my life by coming up with this ruler, but I'm now done with it, so I can live my life outside that aid. So, the hermeneutic paradigm. So I've talked about phenomenology. So if you can go back and remember, phenomenology is all about the taken for granted assumptions that are needed for any activity to occur. And that it involves, it's required for everyday life, and it's required for all activity. And part of the taken for granted assumptions include knowing the context of your assumptions and knowing the context of your statements. So hermeneutics came on and transformed the phenomenological paradigm. And in transforming it, it opened up a whole other area of possible ways of thinking about social life and researching social life, and ways of thinking about how things come together and how they separate. So with hermeneutics, we began to see that the modern turn, which includes the rise of science, the rise of technology, the rise of cities, etc., is a particular way of being in the world. And part of the idea of modernity, is to use Heidegger's phrase, is it talks about the idea of the world as if we were outside and above it. So Mike gave us a good example of the globe. We can picture it. We see it through technology. We see Chris Hadfield and how he pictures how we can see what the globe looks like. And that rests on a certain way of being in the world. So part of hermeneutics is about the dialectic of understanding. And this now posits that understanding is not an entity in the world. It's not just one of the things we do, like we understand, we eat, we talk, we sleep, we drive, and it's one of those things we do, among other things. But from a hermeneutic point of view, understanding is the part of the structure of being It's part of our being in the world that makes possible the actual exercise of understanding at the empirical level. That it's and so that from a phenomenological hermeneutic point of view, we're in the world and objects make themselves manifest to us in ordinary everyday ways. And it's only when we take on a specific relation to it that we take it out and start measuring it, calculating it, etc. But that relies on our being in the world. So hermeneutics says we are being in the very act of constituting an object. So it takes that reflexive turn of phenomenology and adds another reflexive element by saying it relies on us as human beings who are constitutively oriented to understanding. And so now the modern turn is seen as a particular turn on that way of being in the world. The phenomenological method turns to the process by which, of understanding through which things appear. And hermeneutics, the phenomenology of being, becomes a hermeneutics of existence, because you're always applying a way of being in the world. Every way of looking at an object and understanding an object has an implication for being in the world. So, for hermeneutics, and again, this is what's challenging, but for me, the world is not something out there, but rather the whole within which human beings find themselves already immersed. It's what we're already in as part of. We only begin to separate things after we've been, Heidegger says, thrown in the world. So the world is prior to any objectivity, to conceptualization. And world and understanding are inseparable. World has an unobtrusive character. It's there, it's background, and it's only when we start to conceptualize, to try and measure it, it takes that understanding and gets a specific element of it. So one of the ways of describing this, and it's one of the areas I've done research that Jim mentioned earlier, is the whole relation between illness and health. What is illness? Illness objectifies itself. Illness is something goes wrong. You feel the pain. It confronts and forces itself on us. However, health has an ontological primacy. Health is a condition of not noticing, a condition of being ready and open to the world. When we're healthy, we give ourselves to our projects, whether it's our family, our friends, quantum computing, phenomenological hermeneutics. We're giving ourselves to those things. And we're forgetful of ourselves in the giving. When we get a pain, we're pulled back into our bodies. And the world, withdrawing from the world. So pain causes us to turn from the world. Health is giving ourselves, forgetting about ourselves in order to give ourselves to the world. And that would be the unobtrusiveness of the world and the unobtrusiveness of health. So it's a pre-reflective state of being. And this is a quote from Gadamer. Health has a phenomenological structure in itself, a certain way of being in the world. So one of the areas that I research is called the gray zone. So there's a gray zone between the objectifying status of illness, and then we start looking at what its causes are, we study it, and try to find ways to cure it. And what are we curing? So that somebody can forget themselves in their projects. Because with illness, they can't not forget themselves. They can't not forget the pain. So there's a gray zone between the objectifying status of illness and the unnoticed background of health. A gray zone between the methodological primacy of illness, where let's fix it so we can get rid of it, and the ontological primacy of health, which is it's part of our being in the world. So understanding always has a pre-structure for hermeneutics. This is the hard part. Hermeneutics now says that understanding takes place in a part-whole relation, where the one who understands is part of the whole to be understood. What are the implications for this? Part of the implications for this is that the desire for mastery and control now is recognized as one way of being in the world. And that desire might need to be engaged and examined in relation to the need for judgment and wisdom. So one theorist I mentioned earlier, and there's a movie actually coming out about her that's about to be released, I think, in a couple of months, Hannah Arendt and her famous study of the banality of evil and Eichmann. She talked about the human condition. The human condition has three fundamental elements and three realms: labor, work, and action. Labor is about what we do to survive as individuals and as species. It's the biological life cycle. How we continue as individuals, feed ourselves. It connects us to all animal and plant life. Work is about creating things that will outlast us, things that will be there after we're gone. And through work, a world is created that connects us to past and future. So think of the artifacts that have been created in the past that are still being handed down. Everything from Homer's Iliad, right through to great theories, right through to the wonderful buildings we have here, handed down from a previous generation and connect to a future generation. So what world does, it connects past and future and creates a sense of permanence. So from a hermeneutic perspective, the Middle Ages would have had a very poor level of science, but they would have had a strong sense of a world where generations were connected. They could imagine a future generation 7, 8, 10 generations out, because they knew what they were handing on. So every generation has always the option: what do we preserve? I should hold this like this. What do we preserve enough to hand it on and care about the world so that somebody else can take this up, renew it, re-engage it, or it gets dropped and we have no control over that. Action is our capacity to speak with each other without things in between, where it's things, artifacts, mediate our relation to the world. Action is where action and deeds are about how we can speak to each other directly, such that humans have the possibility of beginning something new, of doing surprising and unpredictable things. And through such action, reveal themselves as unique beings. For Arendt, this is the political realm, the public realm. She developed the idea that the modern world, now we're going back to the rise of the 17th century, the 1600s, was the beginning of a world alienation, especially with the idea of progress. Why? Because it already talks about the past as primitive. It's, it's unformed, undeveloped, or not as developed as we are, and the future is full of endless possibilities. So what would the experience of power now look like from this perspective of the human condition? Let's take the work paradigm. The work paradigm is the paradigm where you're producing products. And in that paradigm, the sense of power within is of a human who's outside and above what they're producing and recognizing and seeing. So outside, what is manipulated and controlled? The limits of mastery and control are always contingent. What can't be done yet, what is not known yet. So knowledge is always developed to overcome contingent limits. But that's still within the production paradigm. in the action paradigm, limits are fundamental. Why? Because we're finite beings. Part of what hermeneutics seeks to reconcile ourselves to the recognition that we're finite human beings, that our knowledge is finite, our actions are finite. We're not masters of time and space, not masters of the universe. And insofar as we do that, any action will have unanticipated consequences. So the expectation and planning of finite beings is finite and limited. So here we're recognizing fundamental limits. Limits that are not there just to be overcome, but limits that are part of what it means to be human. Once we get rid of those, we get rid of our humanity. So recognition and reconciliation to fundamental limits are now part of how this research study raises for possibility. And that in turn means learning to enjoy being at home in the world. So the production paradigm says acting to produce a good outcome. But we're finite human beings. So any good outcome will have unanticipated consequences. Just like every invention had unanticipated consequences. I mean, whether it's the, social media, people can connect with each other, but now social media has increased the possibility of bullying. And the action paradigm involves knowing in what way that good outcome comes up against understanding fundamental limits, which includes the idea of what it means to be human. Hannah Arendt has written she's written an essay where she's taken up some of the issues with Heisenberg and Max Planck and talking about how in the quantum world, she uses a quote from Heisenberg, that the human encounters themselves and what they're making. And the idea, Arendt talks about the idea of being at home in the world. And we know there's something out there about somebody wants to make a colony on Mars or something like that. Well, the world is where we are able to give ourselves to it, move naturally. We don't need a special suit. We don't need, we understand how we can build our projects. We can connect to past and future. The idea that we can conquer through both the development of scientific knowledge and the development of technology and the intertwining. We've conquered the idea of space where we can fly, imagine being outside, but that can only be encountered inside a suit. Inside a special suit or inside a special capsule. So from a hermeneutic point of view, that's actually the exclusion of the world in the full human sense of the term that has been experienced as part of the world. So power, in this sense, is the ability to act for a desirable outcome, which includes reflection on the desire. What is the reflection on the desire for more power, more control? What does that do? What do we need it? And reconciling ourselves to the world within which one acts. So, human well-being. So this is possibility. This work, for me, what was interesting is all of a sudden there's a way, despite our various specializations, for me to bring together issues of knowledge, truth, ethics, politics, and relationships, to see how they can be brought together in various kinds of research. So, coming to terms with finiteness. So this would be one of the claims, and I just offered as a claim. The illusion of science is that life is completely objectifiable, and that is a dangerous human overconfidence. It's a dangerous human overconfidence if it does not also remember that it's finite human beings who are imagining this. So this also means you have to imagine how humans can give themselves to overconfidence. We give ourselves to overconfidence. That's how we learn from mistakes sometimes. We suffer as a consequence. But we should remember that in relation to collectively our projects that we're engaged in, our projects that we say are important. Wisdom includes knowing we don't know, famous Socratic phrase. So now, from this hermeneutic perspective, we need to balance, preserve the balance between the knowledge made available by the objectifying science and the knowledge that cannot be objectified. I.e., it's not a matter of, well, we don't have the opportunity to objectify it yet because it's intrinsically non-objectifiable, but it can disappear from the horizon from within particular paradigms. So I was going to do this, but this is just an idea of the kind of more recent research I've done, is a case study on Plato's Gorgias. And Socrates, Gorgias, has three interlocutors he engages. The Gorgias, then Polus, who was a famous rhetorician in ancient Athens at the time, and very powerful, very rich, very well known. And Socrates engages him in dialogue. Then his student is insulted by the way he thinks Socrates is treating his teacher. He jumps in. And then they talk about why you might need power. Polus says, to avoid suffering. Socrates says, you only need power to avoid wrongdoing. You're better off to suffer a wrong than to do a wrong. Polus says, no, you're better off if you can do a wrong and get away with it than having to suffer. So Socrates introduces the possibility of suffering, that you might be better off suffering. The dialectical analysis would try to say which of these positions is true, which is right, and how can that be demonstrated? Another example they use in the dialogue, are we better off being punished for the wrong that we do, or better off getting away with it? Polus says we're better off if we can get away with it. And we're literally meaning better off, not saying what you should and shouldn't do. They're just describing who's better off. And Socrates says, no, you're better off being punished. So anyway, that's all by way of saying that was the most recent example of a, now I would have to go through that study and demonstrate the dialectic that's used in analyzing it, because this cannot be tested by empiricism. It can only be tested in terms of its truth through the method of dialectic. So, and I think that's it.
Thank you, both Kieran and Kayla. I'm sure both of the speakers are open to questions.
No.
No. Please. Could you find your way to a mic just so that others can hear this and be recorded?
So this is for Kieran more closely. So are the prime numbers real?
Who's asking a question? Sorry?
If you could come to the mic, we're recording this, so it would help us record.
Okay, so I want to know. Oh wait, sorry.
Yeah, go ahead. Come on. Come on.
Okay, so I want to know, do you think the prime numbers are real?
For me, numbers, the reality of numbers are real within a language game. So I would say within the mathematics language game, they're real. And I mean, so I would have to ask then, in what sense do you mean real? Do you mean like they exist, that they exist independently of whether we discover, or whether we have a world and a language to talk about them?
Well, yeah. So I'm thinking of crypto, because crypto
covered RSA briefly.
Right.
It seems like if you lock something down, crypto makes the assumption that you can lock something down with this mathematics, and like you can, put it away in a box, and like some alien civilization could come along in 1,000 years and not be able to crack it because of the hardness of the problem that you've locked it down with. But even if like your civilization, your whole language of mathematics and everything has gone away. So it seems like there is some thing that is not connecting between the two sides of your lecture.
Okay, no, I mean, there's certainly, I would say that that's true, that part of what, that there is a gap, a creative tension between the two sides, and part of that is already in relation to the kind of assumptions that I'm bringing that helps me articulate this, but also helps me do my research, and part of the assumptions that Mike brings to what he's doing, and he articulates. Now, I would say that that gap exists in relation to how it's possible to understand any phenomenon. Mike, and how we would bridge that gap, to use the title of the lecture, would be we would try and engage in dialogue. And I would ask then what if you were asking me a question that was about testing an empirical, or testing empirically some mathematical theorem, I would say, well, then that has to be done within that language game. I don't know if you want to take that.
Thank you for your talk, appreciate it. My name is Robert Milligan, and I'm from the community, and I've worked off and on with the university over the years, and I'm the main initiator of what's called the Center for Society, Technology, and Values here, among other things, and I've been involved in the Center for Knowledge Integration, etc. First of all, the idea of lecture and those who receive, I think this is somewhat passé because knowledge is changing so quickly and so on. I think professors need to accept the idea that maybe need to involve their students more. With respect to paradigm shifts and also shifts of belief, I really think this is extremely problematic because, you just take Republicans and Democrats in the States, or the extreme conservatives we have in Canada here, and the rest of us, and how holding on to belief systems and ideology is problematic. Similarly, in the science, holding on to discipline, sort of being uncomfortable with, with the new paradigm, and not eagerly embracing it. I thought there was a concept called curiosity, but it seems, no, it's just holding on because it's more comfortable. And somehow things have to be such so we can better deal with the effects of technology, that not only is our knowledge more integrated, but we shift our paradigms of knowledge so we can better see the more and more powerful effects of what we're doing. So this creates problems of old professors who hold on the paradigm and interfere even with upcoming professors, deny them tenure, etc., unless they go along with the old paradigm. These are serious problems. What do you do about them? Our technologies are potentially causing more and more problems with them, coming together and integrating, sometimes inadvertently. There's an article, was it 20 years ago in Wired magazine about, these various technologies, genetic engineering, AI, and so on. And I worry very much, too, just to finish, about artificial intelligence and it displacing human beings because we have the wrong image of human beings. If you, as Michael Higgins does, recognize the mystical tradition, there's an infinity within. We are limitless, if you like, okay? And then even Pierre Teilhard de Chardin, in a phenomenal way, suggests we expand towards allness like God is. So there's being limited, I think, is problematic. It means we're more likely to be displaced by artificial intelligence and so on. So there's a few points.
So I did try to highlight some examples of, ultimately science is a human pursuit. And I was trying to highlight some of the sociological, just anecdotally, I'm not a sociologist of science, some of the human aspects. You know, we'd like to think that, you know, we're very objective, but we're naturally not. So if this A implies B and B is unpleasant, then not A. That's just how we instinctively work, and we you know, but we use our brains to sort of control these instincts and try to be objective, but it's certainly far from perfect. But I don't have any easy solutions for how to have more objectivity and fairness in the world.
The only thing I would add is that your point, you're raising a phenomena, and from my work would say, okay, look at those occasions when people hold on to things, even when there's something new emerges, and how they, no, but it's the, yeah. So, but then that's a phenomenon to be examined, and that needs to be understood, and needs to be, and what are the stakes at place in understanding that, such that, and this, we don't have to, we can go back further than Socrates to know when he was raising questions, and many of the Athenians found that uncomfortable, so he was executed. Now, so there's not as part of the human condition, theorizing, being open is a very, very difficult state to achieve, to be truly open. And Gadamer calls that the person who's the experienced person who knows that the future is open and recognizes the finiteness of their understanding. But that's a challenging prospect. I see. Okay, yeah. I mean, that would be a separate talk and a separate debate. We could talk about that.
Yeah, I think we encourage our students to challenge us.
So one of the questions that I have around, I'm confused about the terminology in quantum mechanics, because we talk a lot about, you know, if we observe the state of a particle or something like that, and I don't understand what the word observe means in that context, because I think it's confusing. Like, there's some people who are like, does that mean that humans need to see it, or what does it actually mean when something is observed?
Yeah, so it's sort of a simplifying assumption that we make just to make it digestible. It's similar to what Kieran was saying, where we just try to separate the observer from what's being observed. In reality, of course, we can't perfectly do that. You're alluding to this measurement problem that people are still arguing about intensely in quantum theory. And there's no consensus on how to manage it. It could be an interpretational debate, and not an actual physical debate. Again, we debate about that as well. So the problem is the following. If you actually, I was sort of treating the observer, humans, as somehow outside of this game, right? Because then it just becomes a much more easy to swallow game. But if you actually just acknowledge that we're atoms, made out of atoms, which are quantum particles, and you extend these just extrapolate them in the completely natural way, when I actually observe something and collapse it into one or the other with some probability, if you actually treat me as a quantum system and maybe imagine some other observer outside watching me observing, put me in the box, maybe have someone else outside the box watching it or not, then I become what we call entangled with the universe evolves, or what's inside the box happens to be a human being observing an atom, evolves to a combination of the human seeing it in the ground state plus the human seeing it in the excited state. Or there's the famous Schrodinger cat example, where you could have a particle in the excited or ground state, and if it's in one state it releases some poison and then kills a cat, and if it's in the other state it doesn't. So you have if you just treat this, forget about it that it's cats and whatever, it's just a bunch of atoms. You just, you know, without worrying about it, just treat it like a bunch of atoms. But then you describe, what you're actually describing is a combination of the cat being dead and alive at the same time. That's what quantum theory tells you. And you can put observers in there too. That's one of the things that bothers some people. This sort of approach, it's a realist approach to quantum theory, is often called the many worlds or parallel universes interpretation, where you can treat these as, you know, I think it might have been John Bell who said, for all practical purposes, it's as if you collapse into one of these different universes and you can start assigning probabilities. But in reality, what the theory tells you is all these universes, all these realities are existing in parallel. And you only ever, you know, people say, how come you never see dead cats and alive cats? Well, there's no observer that sees a dead cat and a live cat. You have a superposition of observers seeing alive cats or dead cats, which is what all we ever see. So there's no real contradiction there. It's actually a very common interpretation of quantum theory, which bothers some people, so then they think something's got to be wrong with the paradigm because it seems so shocking. I'm personally not shocked. I mean, I'm fine with it, but I don't know if that answers your question. So observing simply means interacting with the system and extracting some information about it. But fundamentally, you know, if you put the observer in the box, then it doesn't collapse it into one or the other. It evolves into a linear combination of one event or the other event. And there's some other observer, hypothetical, say, seeing all this happening or imagining all this happening and knowing that inside the box there's a dead cat and an alive cat. You're really probing one of the more sort of contentious or interesting interpretational issues with quantum theory.
So, Kieran had you mentioned one phrase from another. I will paraphrase it because I don't quite remember it, but basically said that in the quantum world, the humans create themselves. It's not exactly what you said, but it sounded that.
Encounter themselves.
Encounter themselves,
Yeah.
Thank you. And it made me
And she was citing Heisenberg there.
It made me remember the Penrose book on The Emperor's New Mind, where he was trying to understand the brain and how perhaps what we do have here is a quantum computer already. Is that the limit of why we cannot build right now a quantum computer? Because in fact we would be creating ourselves?
No, I don't think that's a fundamental obstacle.
organize his life around avoiding doing it. And develop dialogue and dialectic as his way of trying everyone assumes this is the way to do it, and it actually can challenge that. So that's the distinction between brain and mind.
This ties into what originated with the Big Bang and expanded outward from there. That people, human beings, are not just in the universe, but that we are part of the universe. I'd just be interested to know what either of you have to say about that, to help me understand it.
I'm not sure what the distinction is supposed to be between being in it or part of it.
I guess I'm not sure either.
Okay.
It's all new to me, and I do different. Part of exploring life is coming to things like this, and listening to different stuff. Well, I guess I'm interested in like this. If there is a way to think of that in terms of the quantum world, or in terms of what you said, something, or Kieran said something in your talk about being in the world and observing ourselves. And I just wondered, do you find any distinction at all? Maybe there's no distinction. Just like if I think of the universe as a box, just mentally conceiving it, are we part of the box, or are we merely in the box? Or is the box a solid thing? It's just, there's two great minds in front of me, and I just had to ask the question.
Perhaps another way of reframing that is, and tell me if I'm wrong, but are we being shaped by the universe, or are we shaping the universe? Well, I mean, you could frame it that way. You could frame it that way. You could say, I am just wandering around, and my behavior is simply a reflection of what's acting on me. Or you could say, I'm wandering around and I have some choice, and I can shape the world around me. So it's always changing.
I mean, and just from my perspective, what both sides of those questions would be assuming a kind of a production paradigm. Whether you're outside the producer, acting on it and changing it, or whether you're the product. And so it would be an example of working out possibilities within a production paradigm versus an action paradigm, which would then say that it would change the possibilities for thinking on that issue. And part, again, and well, I'll just leave it at that.
So
Sorry.
So a related point, which may be related, is that what quantum theory tells us, and classical theory tells you, if you're really, really careful, you can observe the universe without actually changing it, or you could, observe it, disturb it as little as you'd like, but still learn it. Quantum theory says you can't. Because the more you learn, the more you try to observe or learn about the universe around you, the more you have to disturb it or change it. You ultimately become entangled with it in a certain way. So the new paradigm does say something different about our ability to sort of passively.
You say entangled, to me that involves like two separate things becoming entangled.
Right. Us and sort of the rest of the universe, inevitably. Yeah, we can't be perfectly decoupled. You can't be perfectly decoupled from the universe and know anything about it. So there is actually a mathematical way of formalizing that idea.
A couple more questions over here.
Hello. Maybe this is an extension to the question just discussed. I'd like to ask that if we think ourselves as one atom system,
Sorry, one?
and one atom
Okay.
system, and how would you define self-consciousness? Because we are the system and we would be measuring ourselves.
Yeah, I'm not sure a one atom system can be conscious. I don't know, it might have to do with some, Turing's ideas where there's a certain minimal amount of complexity to be able to do certain information tasks. And what you have to be, after sufficient complexity, you can be what's called a universal Turing machine and so on. And I mean, there's intermediate things, but so there might be enough internal degrees of freedom with it. I don't know, but I don't know, to define a Turing machine, I don't know. It'd have to be a pretty big atom. But although we don't, it depends how big the atom is.
So in general, how do you define self-consciousness?
I don't know how to define consciousness. So yeah, people say, can computers be conscious? I'm like, well, there's different approaches. I mean, neuroscientists and psychologists and so on, and try to define consciousness. And so then I get to my mathematical instincts. So I'm like, well, can you define what you're talking about? And then I can analyze the definition and the system and tell you if it's conscious. But the hard part seems to be define. There's different ways of trying to define the feature, the key features of consciousness.
And one of the ways within the work I do would be that it's how your ability to talk to yourself. So George Herbert Mead talked about the growth of the self and the having a self as having both an I and a me. And me is how you've been shaped, etc. As he's an American pragmatist from socialization, etc., etc., etc. And the I is because you still have the ability to talk to yourself. So the I is you actually have the ability to act on that. And so that you can, and of course, Arendt, Plato, Gadamer, etc., Blum and McHugh, talk about dialectic as that conversation between me and myself. So it's fundamentally, it's a social conversation, it's shaped by language, but it's a conversation between me and myself. Yeah?
With yourself. With yourself.
And the world.
I had a question for Mosca. I didn't quite follow the Alice and Bob example, the entanglement for how does that actually play out in the game approach? How do they actually, what's the strategy such that they get over 75%?
How do they actually win the game with entanglement?
Yeah, how do they use this?
Well, I won't go through the exact calculation, but physically what they do is they have a stream of these entangled pairs. So they have what you do is you take two atoms or any two quantum particles that can store a bit. You prepare them in the 0, 0, plus 1, 1 state, and they each take half of this thing with them. And they store a sequence of these pairs that are very strongly quantumly correlated. And then if Alice gets a 0, she does a rotation and looks at the atom. If she gets a 1, she does a different rotation and looks at the atom. And Bob does exactly the same thing. And then they just output what they measure.
So it kind of
And
sounds.
that allows them to win the game 85% of the time.
It kind of sounds like they're cheating because they're communicating.
But they're not. Like they're not. They're not. This is sort of prior conspiring, but in the paranoid experiments, they space-like separate them. So if you believe in special relativity, they don't have enough time to communicate. So again, if you're in a classical paradigm, again, you're trying to cheat people who don't know about quantum theory. Is another way of looking at it. So to them, you're clearly not communicating because you're space-like separated, or you're in sealed rooms, with lead walls. So you're clearly not communicating. But quantum theory allows you this extra trick, which you can't communicate with entanglement. But you can win this game. So it's something, it is not as powerful as communication in any case. Sorry.
You have to come up to the microphone.
You mind?
Why isn't it 100% computing? If they thought that why isn't it 85?
It can't. I mean, there's a proof, but it's not that. I don't have an intuitive argument for it. But this protocol I gave you can't achieve 100% correlation. There's another. Well, there's what people call a non-local box, which is somehow even more powerful than quantum theory. That does let them win 100% of the time. But we don't think they're physical. But people studying the foundations of the paradigm study this hypothetical box, which doesn't let you communicate, but you can still win this game 100% of the time. So there exists a hypothetical magic box that lets you win this game 100% of the time, and it still doesn't let you communicate. But quantum theory, as we know it, I mean, I can show you the calculation after, but you can actually prove that you can't go further than this, 85 point something percent.
With communication, if you were communicating, you could win 100% of the
Yeah,
time.
if you can communicate, it's trivial to win 100% of the time. But this hypothetical black box is something which is weaker than communication and lets you win 100% of the time. But it's more powerful than quantum theory. So we don't think they actually exist.
Okay, one more question.
Listening to both of you speak suggests to me that what we're moving into, or the new paradigm or the language games we're talking about, it almost suggests to me a sort of a re-enchantment of the universe, of which the modernity, particularly through Weber, saying the world is, we've become disenchanted. What you're talking about suggests to me it's almost going back to the ancients who had an unreflective, if you will, relative to today, an enchanted world or enchanted universe. I'd like you to comment on that notion.
I mean, for me, I know what you're drawing on. Max Weber, famous sociologist, talked about the rise of science, and in the context in worlds that where the modern scientific development hadn't taken off, there was all sorts of explanations: ghosts, leprechauns, religion, etc. But then, with the rise of science, we're in a better position to control the world and find out the causes of things. But as a consequence, it's going to be disenchanted. The magic is disappearing because we're looking at causes, etc. My work would say, well, in a way, Weber's understanding is in some ways prophetic in how things are developing. But that's not now with the possibility of multiple realities, multiple worlds, that it's possibility to see a place for enchantment again, but it does mean that resistance to that assumption that that's the only way to be in the world.
Reminds me of something Neil Turok often says, in that physics is magic that works.
Well, just to follow up on that, a small comment that we talked about, let's say, simplistically, the ancients or the pre-moderns talking about leprechauns, talking about angels, devils, etc. But in certain ways, one of the things I think that Einstein was perturbed and used the word spooky deliberately was that here we're creating things called entanglements, that somehow something over there and over there are entangled, but they're not communicating. We can't talk about objectivity per se, because in a sense we don't know, because the observer already is affecting it. The ancients didn't spend much time in trying to find methodologies to objectify their world, but actually to live in the world, to experience the world and describe it, which I think is happening in modern thought, whether it's philosophical thought or in scientific thought, particularly in physics. that's, I leave that as a comment.
Thank you.
It's a good thought to end on, and I would like to thank Dr. Mosca and Dr. Bonner for sharing their expertise with us, for a very enlightening talk this evening, and for addressing questions that produced some pretty thought-provoking issues. So thank you all for coming out this evening.
Yeah.